Hello AP Calc class. We are going to take a look at a rule for calculating some limits, and it's called L'Hopital's rule, and we'll apply it in certain situations where we get an indeterminate form is what we would call it. So we're gonna look at some different indeterminate forms where L'Hopital's rule would apply, and then we'll show how we can apply that and calculate our limits. Okay, so it says we return to our study of calculus started limits again. So recall some of these problems that we've looked at before, and really our first approach usually was going to be to substitute directly in whatever the x value is approaching. If we plug that directly in, sometimes that's the easiest way to get the answer. Many times it yields an expression that's undefined, or what we're going to say here when we see that we get 0 on top, 0 on the bottom, that's going to be one of our indeterminate forms. That's probably the most common indeterminate form, is when we get 0 on the top and on the bottom. So there's going to be a technique we can use called L'Hopital's rule when we get an indeterminate form. And this one, as we're approaching infinity. So you can see like this is a quadratic that would be opening downward. So as x would approach infinity, we know that parabola would be dropping, and so you can kind of see that if we have a negative 5x squared, that's our leading term, and so the numerator would be going to negative infinity, and the denominator, that would be, parabola opens upwards, so that would be going to positive infinity. And so this expression, if we think about it the way it's expressed right now, when we plug infinity in the numerator denominator, we're going to get negative infinity over positive infinity. That's another one of our indeterminate forms. Okay, so L'Hopital's rule would apply to both of these. All right, so that's, I guess, what we're showing here. We would get 0 over 0 here, and we'd get negative infinity over infinity for that one. So each of those are represented here in our indeterminate forms. Like I said, 0 over 0 is probably the most common, but then if you have the infinities, whether they're positive or negative in the numerator and the denominator, those would be your other indeterminate forms. There are some other ones as well that we really won't discuss in AB calculus. Okay, so it says, notice how the two limits we were introduced at the top of the page could be, we could take care of those by some factoring and canceling, which is the technique we had used up to this point. There are going to be some, other functions where factoring doesn't work, and so we'd still get an indeterminate form, and they give us a couple of examples that involve some of our like trig functions or our transcendentals like e to the x or some ln sometimes. So what we're going to see, it says they cannot be solved using factoring or any other algebraic technique, yet their limits do exist, and they kind of show the graphs of each of them. As we're approaching 0 here, we can see there is a value for that limit as we approach from the left and from the right. And same with this one, as we go to infinity, it appears that our graph is going to approach a certain y coordinate. Okay, so let's examine what that technique is. It's called L'Hopital's rule. And so if we have one of the following cases where we have a 0 over 0 or infinity over infinity, positive or negative, either numerator or denominator, then what we can do is, if we're taking the limit as x approaches some constant value of something that's and these apply to functions that are like a rational function typically, okay? And maybe you have, maybe not polynomials in the numerator denominator, maybe you have a trig function or an e to the x like we saw. But if, when we directly substitute, if that yields one of these indeterminate forms, what we can do is we can take the derivative of the numerator and the denominator and then substitute that constant in. If we get another indeterminate form at that point, we can do a derivative again, a second derivative. Okay, so that is what we're gonna show here. Okay, so with part A and example 1, the first thing we want to show is that we are going to get an indeterminate form. So the AP exam is a little bit picky on how you show this. They don't like you to say it equals 0 over 0. So what we try to do instead is we're going to show that this just yields, so they usually use like an arrow. So as we substitute, and you're doing maybe some mental substitution here, what you can do is just do that yield arrow. You can do your scratch work in here, so you're going to have 3 times 4, that's 12. And you're going to have minus 7 times 2, minus 14, plus 2. So you can see, okay, I get a 0 there. And then in the denominator, that's 0, 2 minus 2. So we see, and when we show this, now the next thing that we really want to write is, okay, that gives us an indeterminate form. So if we're doing a free response question, then we want to state, okay, this gave us one of our indeterminate forms. Now we can say using L'Hopital's, and let's just make sure that we say, and obviously this section is kind of focusing on L'Hopital's rule, but if we just came across a free response question and we saw this, and we're like, oh yeah, I got to use L'Hopital's rule, you want to state that that's what you're doing, and then rewrite that limit expression again. So now you want to rewrite it and say, here's why. I can just change this and say, well, now it's going to be the derivative of the top, which is now going to be 6x minus 7 on top. And on the bottom, it's going to be just the derivative of the x minus 2 is just going to be 1. Because if you just all of a sudden write that and you don't really say, why you're changing it, they're going to probably not give you credit for that. Even if you get, you'll get probably the answer point if you get the answer right, but your process, if you don't explain what's happening, you wouldn't get that point. So if you're like, ooh, indeterminate form, what do I have to do? So you want to remember this name. You want to state that you're using L'Hopital's rule there. And then rewrite your limit. Okay, make sure you state what the limit is again. You're still doing that. Okay, so we're taking the limit of this now. Now we can substitute in. It's going to be 6 times 2 is 12 minus 7 is 5. And so we just get a value of 5 for that one. Okay. So that's how we apply L'Hopital's rule. First we show, oh yeah, we have an indeterminate form. So now we can apply L'Hopital's rule by taking the derivative of the numerator and denominator and then substituting that value in. Okay. All right, next one. So if we plug a -3, clearly we're going to get a 0 on top. And if we put it in the -3 in the bottom, it's going to be 9 minus 5, which is 4. Square root of 4 is 2. 2 minus 2 is 0. Okay, so now I'm going to say it again, using L'Hopital's rule. So using L'Hopital's, now if I say that, then now I can just rewrite my limit expression having taken the derivative of the numerator and denominator. So on top, I'm going to have a 1. Now in the bottom, we've got that square root, so I'm going to just do a little scratch work up here. So if I have x squared minus 5 to the 1/2 power, right? And then minus 2, that's just going to disappear because that's just a constant. But if I do the derivative of that, I would have 1/2, and then I would have x squared minus 5 to the -1/2, and then I would have, I have to use a chain rule there, so then I have to multiply by 2x. Okay, so that's what I would have. Now let's see what happens if I substitute a -3 into this expression. So I'm just going to have 1 on top, right? On the bottom, I'm going to have 1/2, and then I'm going to have, it'll be 9 minus 5, which is 4, and to the -1/2 power, which means like, it's going to be like 1 over the square root of that. So I'd have 9 to the -1/2. Well, the square root of 9 is 3, so if it's to the -1/2, it would be 1/3. And then it's going to be times 2 times -3. So that's going to be times -6. And so when I simplify this, I think I'm just going to get, let's see if I did that right here. So I got 1/2 times 1/3. So that's 1/6 times -6, which is just going to be negative. So I think for this, I just get -1. Okay? So just make sure that you are, stating what it is that you've done to apply that rule. All right? All right. I think we're going to have something similar here where we're just going to get a 0 over a 0, and then we'll apply L'Hopital's rule. And we can do it, sometimes you can need to do it more than once, but I think in this case we don't. I guess we can go through this one too. So if we put our 1 in here, 5 minus 4 minus, so that's 0. And on the bottom, 10 minus 1 minus 9, which again is going to be 0. And so we'll say, just make sure that we say we're using L'Hopital's. And then now we're going to have our limit as x approaches 1. And on top we would have 20x cubed minus 8x. And then on the bottom we would have -1 minus 18x. All right, so what happens here? So if I plug in a 1 there, see that's just going to give me 12 on top, and on the bottom that's going to be negative 19, and there I've got a value. So 12 over negative 19. Okay. All right, example 2. So we've got a trig function here, and so when I just directly substitute that 0 into there, so cosine of 0 is 1, and 1 minus 1 is 0, so I get 0 on the top, and on the bottom that's obviously 0, and so I know this is getting kind of old writing this all the time, but we should get used to, because if you run across one of these, if you're just doing a worksheet of these problems, I guess maybe it's not, but when you come across a free response question, you do want to explain why it is that you're changing this, okay? Oops. Change colors. Okay, so now we're going to rewrite our limit. Limit is x approaches 0. So now I'm going to do the derivative of that cosine of x minus 1. Remember, derivative of cosine is negative, negative sine of x, and then the minus 1 would disappear. Then on the bottom we'd have 2x minus 1. And now if I plug in my 0, I'm still going to get a 0 on top because sine of 0 is 0. But on the bottom I do get negative 1. And that's on indeterminate form. 0 divided by a constant is 0. So that would be our limit in this case. That would be 0. Okay. Next one. So we've got a limit as x approaches 1. So ln of 1, remember, any log of 1 is always 0. So that's 0 minus, and then we're putting in a 1 there, so 0 minus 1 plus 1, so that's going to be 0. And then on the bottom we've got e to the first minus e times 1, so e minus e, so this yields a 0 over 0. So using L'Hopital's, we're going to rewrite this limit as x approaches 1, and remember the derivative of ln of x is just going to be 1 over x. So I've got 1 over x on top, and then derivative of x is minus 1, and that plus 1 is going to disappear. Derivative of e to the x is e to the x, and then we have e times x. Now, this isn't e to the x, this is e times x, so e is a constant. So the derivative of, it's like if it was minus 2x, right? We'd just have 2 when we do its derivative. If it's ex, it's just e, minus e, right? Okay, so now I'm going to plug in my 1, and I'm going to get 1 minus 1 on top, which is 0. And on the bottom, I get e minus e, which again gives me 0. So this yields 0 over 0. And so now I'm going to state again that I'm going to use L'Hopital's rule again. So I would restate this. I would say, I'm using L'Hopital's rule again. And then I would rewrite my limit again. Limit as x approaches 1. And then I would have to do my derivative of this piece and this piece. So derivative of 1 over x would be negative 1 over x squared. And then the minus 1 is going to disappear because that's a constant. And the derivative of e to the x in the bottom is e to the x. The derivative of this e is 0 because that's a constant. Okay, and now I can plug in my 1, and I get negative 1 on top, and on the bottom I get e. So really the answer to this limit is negative 1 over e. Okay. These last couple, I'll maybe talk through this one, and I think this one's basically similar. So, all right, so in this one, for part C, if I were to plug in infinity, right? So if I'm plugging in infinity, and this has a negative 5 for my leading coefficient, I'd have negative infinity here, and I would have positive infinity here. So since that's an indeterminate form, we'd say using L'Hopital's rule, we'd rewrite our limit and derivatives of each. And again, because leading coefficient's negative 10 here, and this is a positive 6, we'd have negative infinity over positive infinity again. So we're going to do one more, L'Hopital's rule again, and then I'm left with just negative 10 over 6. So derivatives again, and then that's just going to be, it's just a constant now. So negative 5/3 would be my value there. Okay, and then for this last one, okay, so if I were to plug in infinities, I would have on top, I would have a positive infinity, because again, that's just a parabola. And then here, e to the, it's an exponential, and so that's going to be going to infinity. So e to, that's my highest degree is this e to the 5x, so I'm going to be getting, that's going to get infinitely large, so I'll have infinity over infinity again. So using L'Hopital's, I'm going to separate this. So L'Hopital's. So when we do that one, then we're going to end up with 8x minus 5 over 5e to the 5x. 5e to the 5x, because remember, derivative of e to the u is e to the u du, so that's your chain rule, right? And so e to the 5x times the derivative of 5x would be so I have that 5 there. And then derivative of ln of x is going to be plus 1 over x. And, oops, I forgot to write my limit there. So limit as x approaches infinity. Sorry, it's running out of room here. But if I take the derivative, or if I take the limit of this one, I'm still going to get a positive infinity. And again, a positive infinity is what that's going to yield. So let's do it one more time. L'Hopital's rule is going to apply one more time. So we'll have, oops, sorry. All right, so L'Hopital's rule, and then we're going to have the limit as x approaches infinity. And on top, this will just change to an 8. And then on the bottom, we're going to have 25e to the 5x. And then that would be minus 1 over x squared. When I do the derivative of the 1 over x, it'd be 1 over x squared. So now this is going to become what? So we're just going to have an 8 on top, right? Now on the bottom, what's going to happen here, we're still going to have, this expression here is going to grow to infinity. This is going to kind of go down to 0. So really we end up with 8 over infinity. And if we have a constant, remember, if we have a constant over an infinitely large number, that's something divided by something very large, it's going to go to 0. So this ends up having a limit of 0. Okay, so that's what we got for L'Hopital's rule. So remember, if you get one of the indeterminate forms, state that you're going to use L'Hopital's rule, and then rewrite your limit expression having taken the derivative of both the numerator and denominator, and then try to substitute in again. That's pretty much the gist of L'Hopital's rule.